A tree fell on my power line. I'm recording this a second time. I'm a little bored with it. I don't really want to do it, but it's my job. So I'm gonna record it a second time. And that's all I have to say about that. Let's talk about the forward Euler method. This is the Back to the Future joke, is that we are going to predict what happens in the future based on what is known about the present. Which actually has nothing to do about the plot of the movie. Okay, great. The forward Euler method is kind of crap. We're just going to get that out of the way now. Because here's the thing. It's not accurate. It just isn't very accurate. I don't really know what else to say about that. Now, there's reasons for that. We'll get into it. And some of those reasons are even partly fixable. But the real reason we start with this is not because it's a good method, but because it's an easy method. It's not that crazy conceptually, and it's something that you can implement without a lot of coding sophistication. And it's not useless. In simpler problems, it can work well enough. But really, we're doing this for training wheels. This is so that you can practice the skill of translating math into code, so that you can get the idea of how to structure your data, how to implement time steps, how to analyze numerical error, and ultimately graduate to bigger and better things. That's really what we're trying to do here. So having said that, let's get on with it. The thing is, we do need a method for solving differential equations numerically. They're simply too complicated in the real world. If you have some really simple thing like, oh yes, I have a square plate with a circular hole perfectly in the center, okay, maybe you can do some really clever math and symmetry arguments and simplifications, whatever, and maybe actually get exact solutions. And those problems are not without value. They can be useful models for complicated things in the world, but at some point, you gotta get on to harder problems and be like, okay, what if my sheet is not square? What if it is this curved body panel in a car and there's different stresses on different sides and blah, blah, blah. And next thing you know, you're like, it's literally impossible to solve this by hand. So what do I do? Well, what you do is you solve it with a computer. And if your methods are good enough, then your answers are accurate enough that your answers are useful. And that's what matters about this. So this is not about the search for deep fundamental truths. I mean, some people make it about that, but it's about developing the toolkit that lets you make answers that are good enough. So let's do that. And we're going to do that with Taylor series. Surprise! This is our number one approximation tool. So when we're looking at the Taylor series for a function, if we want to take a little step in that function, say, okay, I know what it is here, but what is it over there? And over there might be in space or it might be in time. Then what we do is we say, okay, here's the value of the function at my current location, and I'm going to estimate the new value some distance h away, and I'm going to do that with this sequence of terms. That'll take the current value plus something that depends on the derivative, plus something that depends on the second derivative, etc., etc. And you keep as many terms as you want based on your patience and your need for accuracy. This is what drives the forward Euler method. And what we do in order to implement this method is we follow the Taylor series, really. You say, here's my value for the present right now. You calculate the derivative of your function. Now, you might at this point object and be like, but I thought I had to find the function. So how can I find the derivative of the function if I don't know the function? And the answer is, hey, this is differential equations, remember? A lot of the times, the equations we have are equations that tell you about rates of change, not absolute values. So it is often possible to get the derivative without knowing the function. Then you have to make a decision as the programmer, as the person writing the code. You have to be like, this is how big my step size is going to be. Now, there are tools, there's information, formulas that can help you choose a good step size. We'll look at that later. But part of the skill you develop is the process of figuring out how big of a step is going to give the right balance between accuracy and a reasonable runtime. Then we actually are just going to keep first order. You throw away all the squareds and cubes and whatever, and you're like, linear approximation, baby. That's all I'm going to do here. And then that gets you the new value for the function. And then you do a linear approximation and you get the next value. You do a linear approximation, you get the next value, go, 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 go. And then you say, okay, that's good. I got my answer. So what does this look like geometrically? I'm going to sketch out a real crude representation here. So imagine like this is the true value of the function. Now, just like for teaching purposes, right? I know the point is that you don't know the function, but there is some correct answer. What we're doing is we're trying to find that correct answer. And given that function, what you do know is you know its initial value. So then you say, okay, great. Here's where my function starts. I need to find out where the function goes. Well, first you start by taking its derivative. And you're like, okay, I got its derivative. It has that tangent right there. And then you take a step forward in the function. So you follow that derivative. Okay, the derivative's a little drunk, but it's fine. Ta-da. Okay, so that was our step, h, and we followed our tangent line. And now you say, okay, great, I'm going to find the derivative at this new point, and that's the slope. And so you draw that tangent line, and you take another step. And then you take another step, and you're like, ooh, now my derivative's 0 at this point, so I'm going to draw a flat tangent line. And this is how you build up the sequential values of the function. You're like, I take some derivatives, I do linear extrapolations of those derivatives, and that helps you draw something that does actually kind of look like the function. It's not super accurate, but the general idea is there. And if we took smaller steps, then this would gradually get closer to the real function. So this is the idea of Euler's method. This is how we do these things. Now, I've mentioned error more than once. We have to address that. The thing is, some of this error comes from the fact that we're throwing away all those higher order terms, the quadratic and cubic and whatever terms in the Taylor series. So the big O notation, remember that from forever ago, is that the error is order of h squared. It's going to be essentially quadratic in our step size. So that's one way of looking at it, is that's a bad thing, because if I take bigger steps, then I get the square of that bigger step as an even greater error. But you're like, can I go the other way? Well, it's not that simple. Here's what you have to remember. You're solving over some total interval from beginning to end of your function, and you're breaking that interval up into steps. Okay, fine. If you cut the step size in half, yes, your error per step reduces quadratically. You'll get 1/4 of the error per step if your step size is halved, but you also have twice as many steps needed to cover the same interval. And because every step accumulates error, every time you take a step, you're getting a little bit more and more and more wrong, then even though the error per step is smaller, the increase in the number of steps costs you some of those gains. You still get a linear improvement, but you only get a linear improvement by shrinking the step size. So you can't just be like, I'm going to take the tiniest steps ever and then it'll be accurate. Well, kinda, but it's also going to take forever to run. So you have to deal with that. Okay, how do we apply the forward Euler method to partial differential equations? When we're talking about the physical world, so I'm not interested in like super deep math theory here, but the physical world, as I kept mentioning in the last couple of videos, is described by partial differential equations. And when we're looking at problems in STEM, okay, in STE, when we're looking at science and engineering problems, what we want to know is we want to know how things change over time. We're like, I have the initial state of my system, but what happens an hour later or a day later or a century later? Well, you have an equation that describes how things change, and so you use this method to find values in the future based on values in the present. That's what we do. Now, there's ups and downs here. Downs is that you have derivatives of multiple variables, and these things are interacting with each other. So on the one hand, you might feel like that increases the complexity of the computation, and it does from one point of view, but it's also an opportunity because often you can calculate the time derivatives from the space derivatives. You can say, I'm going to solve for df dt in my partial differential equation, and as long as I know the positional information, I can then find the time information, and that's very powerful. How do you do this? Well, you use the partial differential equation the way it's written. If we're talking about the heat equation from last time, that was that the time derivative of the temperature was determined by some constant. I think I just called it alpha. And then the space derivative, second space derivative of the temperature. So if we know the initial conditions, if we know the initial temperature at every point in space, which often is very doable if you're modeling a physical experiment or making a prediction from a known starting point, then you can say, I know the values in space, I can calculate the derivatives in space with the numbers that I have, and then feeding those into the equation that will tell me the derivative in time. And that lets you step time forward using those time derivatives to calculate delta f by saying delta f is df dt, which we're solving for here, times delta t. In the example of the body panel, it might be like, okay, I'm putting my body panel in a furnace, and so I know the initial temperature. My panel starts at room temperature, and the furnace starts at whatever temperature. And so that tells me T of x at time equals 0. And then you use those T of x values to calculate your derivatives. Go, 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 go. So you get your derivatives, and you do the Euler stepping. And here's this term that is the delta f that I was talking about a minute ago. So that's how we do this. It's actually not crazy. It takes a little bit of patience with managing the data and not getting confused, I suppose, but it's very, very doable. Okay, to implement it, I said it was doable. How do you do it? Well, you're going to need to structure your data. You're going to need arrays to contain the values that you're working with. And I'm just going to draw this in one dimension. Like, we definitely want to start simple before getting more complex. So we're going to have some array of values. Like maybe here's, I don't know, x equals 0, and then here's x equals 10, and then we're going to slice it up into segments. I can't even count. I think that was too many. It's fine. They don't have to be one wide. So now we have our array to contain the values of the function at each point in space. F of x equals 0, f of x equals 1, f of x equals 2, blah, blah, blah. Now, what you're going to do is use that spatial information. Oh, and this is at 0 time. So we're going to start at the beginning of the problem. Maybe that sounds silly to say, but I'm going to say it. But you can use this to calculate the spatial derivatives. Actually, let me write it this way. I should be more correct. We are going to call this f sub x because this will be the x partial derivative. And then you are going to have some array that holds those derivative values. And at every point, okay, that's good enough. You will calculate these derivatives based on the differences in your values. You're like, aha, yes, the difference between these two guys tells me the derivative of the function right there. And if you need more derivatives that you can keep going, you can be like, all right, so now I need my second x derivative of my function. And you're like, well, I can calculate that as the derivative of the derivative, right? You can. I don't know that I'm going to say you should. This is actually kind of tricky and starts to get really into some of the subtlety of these numerical algorithms for doing calculus. Taking the derivative of the derivative is one way to take the second derivative. But if you're a little bit clever with your math and actually do some math by hand first before just throwing everything straight into numbers, you can find what I'll call shortcut formulas that are actually faster and more accurate. So this is another example of do some math by hand first to make your results better and faster. But anyway, you get all these derivatives. And so you can then take all these values and use them to answer the question, what is my time derivative? And that is important to remember, the value of the time derivative at each place in space at 0 time at the beginning of the problem. So we have our array, and every element in our array is going to be the time derivative at a particular x coordinate, calculated from the x derivatives at that x coordinate. So you do this, and everything is great and fine. Hooray. Now you know your time derivative. Finally, you can do forward Euler. Now you can say delta f is df dt, delta t, and then you can get your new value for f of x one time step later. Bam. And so you'll write those values into an array at your new time, and each of those will be calculated by, again, adding delta f to the previous value in that location. And then you just keep doing this forever and ever and ever until you have your answer. Hooray. It's not insane, but it does require a little planning. Now, that was all linear stuff. And it's like, but you're complaining about the accuracy. Well, I am, because the accuracy sucks. You're like, why not just use more terms in the Taylor series? Then it'll be more accurate. I wish it were that simple. So first, calculating higher derivatives, because remember, the Taylor series doesn't just depend on the variable squared for the second term, it also depends on the second derivative for the second term. So now you have to know how to take more derivatives of your function, and that is just going to make the calculus harder. Doesn't make it impossible, but it does make it more involved. And in particular, the error in that derivative calculation can actually be quite large. So you have now this trade-off where including more terms in principle makes your answer more accurate because you're taking more derivatives into account in your Taylor series, but those additional terms are themselves laden with numerical errors. So the gains, the net gains in your accuracy might be nothing at all. It might be negative, might be positive, depends on the problem, but sure, you're adding more terms, but those terms can be wrong because numerical derivatives are not exact. So what you can do instead of adding more terms is take the terms you have and make them better. You can do the predictor corrector method. Sounds very fancy. It's actually super clever. This is the kind of thing that isn't that complicated, but you're like, someone really smart must have come up with this. I wish I were smart like that. So here's what you do. You use the forward Euler method. You do your time step prediction business. But before moving on to that next value, you do additional calculations to correct it to get it closer to the real function, even though you don't know the real function, because that's what we're trying to find. You're like, this seems like magic. How can I correct my value to make it more right if I don't know what the right answer is? And this is where I'm like, yeah, but smart people work on this stuff. So here's how it works. I stole this image directly from Wikipedia. It's great. Why wouldn't I, kind of? And you have to be aware that there's more than one way to take a numerical derivative. Hoyne's method is this particular kind of predictor-corrector method. So you do your Euler step, you do your linear extrapolation, you're like, here's what I think the next value is. But then you are going to do an average. You're going to average that step you just calculated with a correction. And how you get the correction, this is very clever. So this is the averaging, right? Is you have 1/2 each of two different things added together. You are going to take two different derivatives and combine them. You're like, two different derivatives? How many derivatives does the function have? Well, analytically, one, if it's differentiable. But numerically, you can calculate the derivative in multiple different ways. And two ways that we use here are the right derivative and the left derivative. The left derivative is value of function minus value of function to the left divided by your interval. Right derivative is, wait for it. That's right, it's the value of the function to the right minus the value of the function here divided by the interval. Because we're doing slopes, right? These are numerical derivatives. It's rise over run. But you can say, what is the rise to the left or what is the rise to the right? And those answers will be different if your function is curved. And if your function is curved, that means it has a non-zero second derivative. And that's the whole problem here, is we threw away the second derivative term in the Taylor series. So we're remediating that issue by saying my left derivative and my right derivative, one of them will overshoot the function and the other will undershoot the function because it's curving away from its true tangent line. So one of them goes above, one of them goes below. And that means that in between, their average will be closer to the true value of the function than either one of them. And that's how you do this correction. You create your correction based on the left and right derivative, knowing that one of them overshoots, one of them undershoots. Very smart. Super cool. I wish I were smart, but I'm not, and you're stuck with me. So we're going to get through this together. Let's say. So this is the forward Euler method for dealing with partial differential equations. You start from a known starting point and you work your way forward in time by calculating derivatives. That's how we do the thing. Now, what I haven't really talked about here is boundary conditions. I've mentioned the initial value problem, but what happens at the edges of the box? How do you deal with the sides of your array? That's what we're going to do next time. What we're not going to do next time is to talk about more advanced numerical methods. There's books on this stuff, right? It's not like I'm going to pretend to teach you everything in one day, but this is a good starting point. Just realize that at the end of the day, even if we do clever corrections, we're still limited by the fact that it's a first order algorithm. And if you go to higher orders, like the Runge-Kutta algorithm, which is a fourth order algorithm, you can get way more accurate results, even for functions that are tortuous and curvy and complicated and all that. We're not going to go there in this course, but if you take a numerical methods class, that's the kind of stuff that you'll do. If that excites you, great. If it terrifies you, well, sorry, but that's how it is. Okay, I'll see you in the next video and we'll look at boundary conditions.